And now, the theorem you've been waiting for. Suppose you have two linearly independent solutions to our basic problem. And let's suppose that y hat is any other solution. Then there exist unique constants C1 and C2 such that solution y hat can be expressed as a linear combination of y1 and y2. This tells us that if we have two linearly independent solutions to a second-order linear constant coefficient homogeneous ordinary differential equation, then in fact we can construct any other solution. We've got them all. Two solutions is what it takes for a second-order equation. More generally, if this were a third-order equation, it would take three linearly independent solutions to construct all of the rest. If this were an nth-order equation, it would take n linearly independent solutions to construct all solutions. If you get two, you've got them all. This is exactly what we need. This being such an important theorem, we better give the proof. Set y naught to be y hat of x naught, y naught prime to be y hat prime of x naught for some x naught. Consider the system of equations C1 y1 of x naught plus C2 y2 of x naught equals y naught. C1 y1 prime at x naught plus C2 y2 prime at x naught equals y naught prime. This gives us a system of two equations in two unknowns. By a theorem from linear algebra, this has a unique, this has means existence, and unique means uniqueness. There exists a unique solution C1, C2, if and only if the determinant of the coefficient matrix is not 0. But we know the determinant of the coefficient matrix is not 0 because we've assumed that y1 and y2 are linearly independent, which means that their Wronskian is not 0. And the determinant of the coefficient matrix is equal to the Wronskian. Since y1 and y2 are assumed to be linear independent, the Wronskian at x naught is not 0. Therefore, we get a unique C1 and C2 that solve the system. We're going to set y tilde to be C1 y1 plus C2 y2 for these solutions C1 and C2 to that system. Since y tilde is a linear combination of solutions, it is a solution. Any linear combination of solutions to an nth order linear homogeneous ordinary differential equation is a solution. We also have y tilde at x naught equals c1 y1 at x naught plus c2 y2 at x naught, which is equal to y naught. Y tilde prime at x naught is c1 y1 prime at x naught plus c2 y2 prime at x naught, which is y naught prime. This means that y tilde and y hat satisfy the same differential equation and the same initial conditions. By the existence uniqueness theorem, y tilde must be identically equal to y hat. But wait a minute. If y tilde equals y hat, and y tilde is c1 y1 plus c2 y2, that means y hat is also c1 y1 plus c2 y2 for unique constants c1 and c2. And that's the end of the proof. This theorem allows us to make some important definitions. If y1 and y2 are linearly independent solutions to our second-order linear constant coefficient homogeneous ordinary differential equations, we say that y1 and y2 form a fundamental set of solutions, y1 and y2. Also, the general solution to our problem is c1 y1 plus c2 y2 for linearly independent functions y1 and y2. We can call this the general solution because all solutions can be expressed as a linear combination in a unique way like this. So, suppose lambda 1 and lambda 2 solve the characteristic equation a lambda squared plus b lambda plus c equals 0. And let's also suppose that lambda 1 is not lambda 2. Then the Wronskian of these will be, of the solutions, e to the lambda 1 x, e to the lambda 2 x will be, let's see, we'll have lambda 1 e to the lambda 1 x, lambda 2 e to the lambda 2 x. This gives us lambda 2 times e to the lambda 1 plus lambda 2x minus the product this way, which is lambda 1 e to the lambda 1 plus lambda 2x. We can factor the exponential function out and get lambda 2 minus lambda 1 e to the lambda 1 plus lambda 2 x. This can only equal 0 if lambda 1 and lambda 2 are equal, since the exponential function is not 0. And since lambda 1 and lambda 2 are assumed to be distinct, we can see that this is not 0, which means that these functions, e to the lambda 1x and e to the lambda 2x, are linearly independent. We see that e to the lambda 1x and e to the lambda 2x are linearly independent if lambda 1 is not lambda 2. Remember that the principle of trichotomy for real numbers gave us 3 cases for the solutions of second-order linear constant coefficient homogeneous ordinary differential equations. The first case was real distinct solutions to the characteristic equation. We can now get a complete solution to that case because if the characteristic values lambda 1 and lambda 2 are real and distinct, then the general solution to the differential equation will be exactly of this form. We also get a solution in the complex conjugate case, because if two complex numbers are conjugates with non-zero imaginary part, then those are also non-equal. But it's less clear what it means to have a solution of this form if the values here are complex numbers. So we need to investigate that next. By the fundamental theorem of algebra, if a polynomial equation having real coefficients has a complex valued solution, then the complex conjugate must also be a solution. Suppose that we get complex conjugate solutions of the form alpha plus or minus beta I. We'll assume that beta is positive. We're already covering the negative case by putting a minus sign in there at times. And also, in particular, beta is not 0. We're assuming that we actually have a complex number here and not a number that's purely real. In this case, I want to consider e to the alpha plus beta I times x. Note that this is equal to e to the alpha x times e to the beta x times I. Not much we can do about e to the alpha x. It is what it is. But I want you to recall something. I want you to call something called Eulers equation, Eulers identity. E to the theta I. Do you know what e to the theta I is? E to the theta I is cosine theta plus I sine theta. This is Eulers equation, or Eulers identity. This is pretty important. We should prove this. In particular, I'd like to state this as a lemma. E to the xi is cosine of x plus I sine of x. To prove this, I'm going to use the Maclaurin series. E to the x is 1 plus x squared over 2 factorial plus x cubed over 3 factorial, and so on. This is the Maclaurin series for e to the x. You might also need to know that cosine x is 1 minus x squared over 2 factorial plus x to the 4th over 4 factorial, and so on. Notice that cosine is an even function and all of the powers here are even. Go figure. And sine of x is x minus x cubed over 3 factorial plus x to the 5th over 5 factorial minus so on. Also, sine is odd, and all of the exponents in the Maclaurin series for sine are odd. It follows then that e to the xi is going to be 1 plus xi plus xi squared over 2 factorial plus xi cubed over 3 factorial. I will write one more term, xi to the 4th over 4 factorial, and so on. Now, how do these simplify? We have x times I here. When we square I, we get a minus. So the next term is going to be minus x squared over 2 factorial. On the other hand, I cubed, we can think of that as I squared times I, which just gives us minus I times x cubed over 3 factorial. I to the 4th just multiplies another factor of I on, and so we get plus 1 x to the 4th over 4 factorial, and so on and so forth. We're now going to collect real and pure imaginary terms. The real terms are 1 minus x squared over 2 factorial plus x to the 4th over 4 factorial. And now the pure imaginary terms. We have x, and then minus x cubed over 3 factorial, and so on. It should now be apparent that what we get is cosine of x plus I times the sine of x. And that's the end of the proof. Before moving on with our theory development, I would like to point out that due to Eulers' formula, e to the pi I is equal to cosine pi plus I sine pi. Now sine at pi is 0. Cosine at pi is negative 1. And so e to the pi I is negative 1. This relates in one equation 4 of the most important numbers in mathematics. The development of pi and e, these transcendental numbers, their discovery and use and applications are very important. I, the imaginary unit, is very important. And the discovery of negatives, or even of 1 itself, the unit, is very important in the history of mathematics. 4 very important numbers and ideas, 4 or 5 ideas if you include the separation of 1 and negative 1 as separate ideas, all related in one equation. Let's go back to our complex characteristic values, and suppose we have y1 is e to alpha plus beta I x, and again we're assuming beta is positive. This is e to the alpha x times e to the beta x I. Because of Eulers' formula, we can write that as cosine of beta x plus I times the sine of beta x. There is also the complex conjugate case. And to find that complex conjugate case, all we have to do is replace beta by negative beta. This gives us e to the alpha x cosine of negative beta x plus I sine negative beta x. Remember that a function is odd if negative numbers, negative values come out. It's even if negative signs disappear. So on y2, we get e to the alpha x cosine beta x, because this negative goes away, cosine is even, and this negative comes out. We get negative I sine beta x. So these are our two solutions. They're great because they are solutions. They're lousy because they both involve an imaginary unit. We need to find a way to combine these in order to eliminate this imaginary unit, if we can, and end up with two linearly independent solutions. Remember, our theory says that if you have two linearly independent solutions to the second-order linear constant coefficient homogeneous ordinary differential equation, then you have them all by taking arbitrary linear combinations. We know that if the characteristic values are distinct, then you get linearly independent solutions. So y1 and y2 must be linearly independent, but they suffer a nasty defect of being complex valued. We're going to see if we can remedy that by finding linear combinations of these. Remember, we have a theorem that says that linear combinations of solutions will yield solutions. I'm going to start by taking W1 to be 1/2 y1 plus y2. That's just a linear combination of y1 and y2, and hence we have a solution. If I add these solutions together, with a line underneath to indicate we should add them, this and this will cancel out, and the imaginary part will be gone. These two will combine and double up, but we're multiplying by 1/2. So we get e to the alpha x cosine beta x. We get a solution that is real valued. Now, how do we combine these two solutions to get another linearly independent solution that is also real valued? We'll do something quite similar. I'm going to multiply by 1/2i y1 minus y2. This is also a linear combination of solutions and hence is a solution. The question is, what happens if you subtract? If we subtract the cosine beta x and cosine beta x terms, they're going to cancel out. If I subtract the I sine beta x and the minus I sine beta x, I'll get 2i sine beta x. But if I'm dividing by 2i, the imaginary unit gets canceled out along with the 2, and we get e to the alpha x sine beta x. We have these two solutions. We know they are solutions. They are real valued. What we don't know is whether or not they are linearly independent. That's the next thing we should check. If we can prove that these two functions are linearly independent, then we will be able to write down the general solution in the case that we get complex solutions to the characteristic equation. To determine linear independence, we need to find the Wronskian. So we're going to have e to the alpha x cosine beta x and e to the alpha x sine beta x. On the second row, we're supposed to put the derivatives. Each of those will require a product rule. So we'll have alpha e to the alpha x cosine beta x minus beta e to the alpha x sine beta x, and also alpha e to the alpha x sine beta x plus beta e to the alpha x cosine beta x. One fact about determinants is that if you have a common factor in any row or any column, you can factor that out of the determinant. So we can factor out an e to the alpha x from the first row and another one of those from the second row. I'm going to write what's left over as cosine, sine, alpha cosine minus beta sine, alpha sine plus beta cosine, just to save room. This gives e to the 2 alpha x times, we'll have alpha sine cosine plus beta cosine squared minus alpha sine cosine, and we'll be subtracting a negative, giving us plus beta sine squared. These two terms cancel. The beta factors out. What's left is cosine squared plus sine squared, which by the Pythagorean identity is equal to 1, and we get e to the 2 alpha x beta. Why does this not equal 0? It's obvious that the exponential function can never be 0, but we have also specifically assumed that beta is not 0. The fact that the Wronskian is not 0 means that these functions are linearly independent. The fact that we now have two linearly independent solutions allows us, in the complex case, to write down the general solution. It's going to be C1 e to the alpha x cosine beta x plus C2 e to the alpha x sine beta x. Note that the oscillation in these problems comes from the imaginary part. If we're going to be applying these second-order linear constant coefficient ordinary differential equations to electrical circuits, we are not going to get oscillations within those circuits unless we have some non-zero imaginary component. Same is true for modeling harmonic oscillators. We're not going to get oscillation unless we get complex solutions to the characteristic equation. We've now addressed two of the three cases that resulted from trichotomy. In the case that we have real distinct solutions to the characteristic equation, the general solution takes the form C1 e to the lambda 1x plus C2 e to the lambda 2x. In the case that we get complex conjugate solutions, we get the general solution to be C1 e to the alpha x cosine beta x plus C2 e to the alpha x sine beta x. You need to memorize this. But there is one more case. I'd like to approach this next case by way of example. Suppose I have y double prime plus 2y prime plus y equals 0. The characteristic equation is lambda squared plus 2 lambda plus 1 equals 0, which factors as lambda plus 1 quantity squared equals 0. We get a solution. Lambda equals -1, and hence a solution to the differential equation is e to the minus x. Unfortunately, it takes two linearly independent solutions to these second-order equations in order to construct all solutions, but we only have one. We need one more solution. How are we going to construct a second linearly independent solution? I'm going to use a method called reduction of order. We know that anything of this form, C1 e to the minus x, is a solution. The method of reduction of order says, instead of taking this parameter to be constant, suppose it's a function. What are the implications of that? If y2 is a function u times e to the negative x, y2 prime would have to be u prime e to the negative x minus u e to the negative x, and y2 double prime would be u double prime e to the negative x minus u prime e to the negative x, these two being the product rule applied to the first term. When we apply the product rule to the second term, we'll get another minus u prime e to the minus 2 minus x, and when we take the derivative of the e part, we'll get plus u e to the minus x. If we plug all of this into the differential equation, we'll have u double prime e to the minus x minus 2 u prime e to the minus x plus u e to the minus x plus twice u prime e to the minus x minus u e to the minus x plus u e to the minus x. Now, here we have a u e to the minus x and another one. 1 plus 1 makes 2. And over here we'll have a minus 2 u e to the minus x. So all of these go away together. Now, check this out. We have negative 2 u prime e to the minus x and a positive 2 u prime e to the minus x. These terms also go away together. This whole thing simplifies as u double prime e to the minus x. If we want this to be a solution, we're supposed to get 0. Well, e to the minus x is not 0. That means that's going to happen if and only if u double prime is 0. Now, what functions have second-order derivatives equal to 0? The only functions that have second-order derivatives equal to 0 are straight lines like mx plus b, or perhaps even c1 plus c2x. Our solution y2 was u times y1, which was u times e to the negative x. For us, that's going to be c1 plus c2x e to the minus x, which is c1 e to the minus x plus c2 x e to the minus x. Remember, this is y1 times c1. Could it be that to construct our second linearly independent solution, all we have to do is multiply by x? Our analysis shows that if y1 is e to the minus x, then x e to the minus x is also a solution. But there's one thing we should probably check, and that is, are these linearly independent? To determine that, we calculate the Wronskian. Over here we need the product rule. This gives us e to the negative 2x minus x e to the negative 2x, and when we subtract this way, we'll get plus x e to the negative 2x, with these terms canceling out. And what we get here is not 0. Therefore, they're linearly independent. We deduce then that the general solution is c1 e to the minus x plus c2x e to the minus x. You're right to wonder, is this process always going to work in the case that we get a repeated root or only one distinct real root as a solution of the characteristic equation? Can you always simply multiply the one solution that you get by x to obtain a second linearly independent solution? And the answer is yes. As an example, suppose we have y double prime plus 4y prime plus 4y equals 0. The characteristic equation is lambda squared plus 4 lambda plus 4 equals 0, or lambda plus 2 quantity squared equals 0. This gives us lambda equals minus 2. We write down immediately the general solution, c1 e to the negative 2x plus c2x e to the minus 2x, and we're done. I want you to see that this theory applies not just to second-order problems, but also, why not a third-order problem? Consider the differential equation y triple prime minus 2y double prime minus y prime plus 2y. The characteristic equation is going to be 0 equals lambda cubed minus 2 lambda squared minus lambda plus 2. How do we solve this cubic polynomial equation? This particular problem is pretty easy because we can factor by grouping. If we combine these two and these two, on the first pair we can factor out a lambda squared and get lambda minus 2. On the second grouping we can factor a minus 1 and get lambda minus 2. This gives us lambda minus 2 times lambda squared minus 1, which finally factors as lambda minus 2, lambda minus 1, lambda plus 1. The solutions are lambda equals 2, 1, and minus 1. It follows then that the general solution to the differential equation is c1 e to the 2x plus c2 e to the x plus c3 e to the minus x. I want to consider three cases for unforced oscillations. Unforced oscillations satisfy the differential equation mb squared y dt squared plus b dy dt plus k y equals 0. The fact that we have no external forcing function implies that this is unforced. But we are allowing for resistance, a spring constant, and a mass. M, B, and K must all be positive, let's say, or 0 at worst. M has to be non-zero. In this case, the characteristic equation is m lambda squared plus b lambda plus k equals 0, which has solution lambda equals negative b plus or minus the square root b squared minus 4mk all over 2m. Just as before, the principle of trichotomy gives us three cases. First, if b squared minus 4mk is greater than 0, then we get two real distinct solutions. In this case, you can also see, because m and k are positive, the value that you get after doing the square root will be smaller in magnitude than b. If we take negative b and subtract something, we're going to get a negative. If we take negative b and add something smaller in magnitude than b, it's still negative. So we get two negative solutions for the characteristic values lambda. That implies that in both of our basic functions in the fundamental set of solutions, we have exponential decay, e to the lambda x, or e to the lambda t in this case, where lambda is negative in both cases. You get exponential decay of solutions, and these Oscillators don't oscillate. It's like we're putting the spring and the mass inside a jar of honey and displacing it, and it just goes back to a rest position without an oscillation. These are called overdamped. The case b squared minus 4mk is equal to 0 is similar. You still get two negative solutions, the only difference being one might have a factor of x, which ultimately is forced to 0 by another factor of e to the lambda x, where lambda is negative. So these are called critically damped. They're the boundary case. Only in the third case do you get oscillation. That's where b squared minus 4mk is negative. In this case, the solutions will do something like this. They'll decay away provided b is not 0. B is the coefficient of friction. If there's no friction, you get the oscillations going on forever without a decay. If b is not 0, the solutions must decay away exponentially in this way, but they will still oscillate. These are called underdamped.